Zoom. Welcome to the afternoon session of today. So our first talk will be a review talk, and it's a pleasure to introduce Oliver Schlotterer from Uppsala. Oliver.
Yeah, thanks a lot, Eric, for the introduction. And thank you so much to all the organizers for bringing together this beautiful conference and for giving me the opportunity to speak here. Yeah, the topic of this talk is string amplitudes. Fortunately, with this kind of audience, it's easy to motivate why we should be excited about string scattering amplitudes. First of all, the field started with an amplitude computation or proposal. And furthermore, yeah, string amplitudes have been continuously a valuable gadget to study the low energy effective regime of your favorite string theories. And in particular, amplitudes are key quantities to do precision tests of string dualities, usually at definite orders in the inverse string tension alpha prime. But also outside string theory, there are reasons to be excited about string amplitudes. Say if you're interested in perturbative gravity, you want to, for instance, test the ultraviolet properties of various supergravities, or you want to conceptually relate gauge theories and gravity, then you can use the double copy property of the closed string spectrum, that gravitons are, loosely speaking, squares of gauge bosons. And this, in particular, in the field theory S matrix, we can see starting from string calculation and taking alpha prime to 0. So string amplitudes being a valuable way of understanding the Bern-Carrasco-Johansson double copy of perturbative gravity. And also in math, it's quite common that mathematicians are collaborating with string amplitudeologists, simply because there are similar mathematical fun topics coming up in, say, number theoretic questions and the specific worldsheet integrals we have to do in alpha prime expansion of string amplitudes. And also particle physicists are often joining the table because Feynman integrals tend to have the same function spaces. Yeah, I'm thinking of zeta values, polylogs, elliptic versions, modular functions, more on that later in this talk. Yeah, so these are 3 pillars of motivation to kick this talk off. But most of all, this is a moment to say thank you into various directions. It's a really fortunate time to work on string amplitudes because we had support from so many different directions. So there's first of all in the string theory literature an enormous support, say from the foundations of the Ramon-Evers-Schwarz or the pure spinor formulation of the worldsheet model. There is a continuous inflow of new ideas how to deal with the subtleties of the respective formalisms, new ideas how to interpolate between them to find new models that unify the advantages of both. And also the ambitwistor string theories that we heard about yesterday from Lionel and Freddie. Also those are strong support even for the full-fledged superstring with all its alpha prime dependence. You will see a 3-loop 4-point highlight of this. And yeah, I mentioned this fruitful intersection domain with mathematics. There's a continuum of people whose interests are somewhere between number theory and algebraic geometry. It's usually hard to categorify the individual contributors in mathematics. Maybe Zaghe and Zerbini might be more on the number theory side. Maybe Brown and Dupont are more on the algebraic geometry side. But all this to say, there are various mathematical perspectives that help us tremendously to understand the low energy structure and of string amplitudes. And this flow of ideas goes hopefully into both directions. So conversely, string amplitudes turned out to be pretty inspiring, say, to explore new kind of mathematical structures, new systems and modular forms. So I hope that all this inspiration transfer is seen as mutual from all these directions. Yeah, let me try to get a bit more specific about the mindset and content and outline of this talk. Let me start with a cartoon of a typical perturbative expansion of a string scattering amplitude. So as you know from the opening line in the textbooks, we are, in case of closed string scattering, supposed to go over Riemann surfaces of various genera, sphere, torus, and higher genus version for tree level 1 loop, 2 loop, and beyond. And now at each loop order, we are supposed to integrate over the moduli space, the shape of that surface and the way to put punctures on it, each puncture for one of the external states. And to be more precise, the external states occur via vertex operators, where, say, the polarizations and momenta of the scattering states are stored. And now, depending on which formalism you use, you have a bit more stuff inside the correlator, say B ghosts and certain regulators in the pure spinner, or picture changes in the RNS. I don't want to go into much detail here, but these are some spurious punctures that in the end of the day can be discarded from the correlator if you massage it good enough, at least to the low loop orders that I'm about to discuss. So accordingly, I'm not explicitly referring to supermoduli here. To the loop and leg orders to be discussed in this talk, we do have representations where the odd moduli are gone. Okay, and yeah, from this cartoon of how a string amplitude is computed, the structure of my talk is as follows. I'll spend the first half talking about new results for the integrands, how far you can simplify these correlators with vertex operators and more stuff. And then in the second half of the talk, I will look at the task of doing the moduli space integral. To be honest, I'm integrating more over the punctures than the moduli, but that's a different story. And yeah, we'll tell you some news about what has been done in the alpha prime expansion of these configuration space integrals. That's the structure of this talk. So let's start going into new results on the integrand side. Okay, here's an overview slide from which you can see that at tree level and one loop, we are already in pretty good shape. How well we know the massless amplitudes for the type 1 and type 2 superstring. So several disclaimers throughout the talk. It's massless states that I will scatter. It's for the moment in 10-dimensional Minkowski, though we are obviously all burning to take this to the ADS and so on. And yeah, I will specifically talk about 2-loop 5-point and 3-loop 4-points, where we have new simplified results for these correlators, free of spurious locations of BGOs or PCOs. And yeah, this is what I will describe in detail in the first half of this talk. Now, I do promise closed string amplitudes, but maybe it's quite economic if we truncate the problem to an open string calculation. So for the integrand / the correlators, this can be done using chiral splitting. So we would like to decouple the left and right moving worldsheet degrees of freedom, which at tree level is no problem. But starting from one loop, there is naively a coupling of the left and right movers. Namely, they share a zero mode, which you can interpret as a loop momentum. Literally, the loop momentum in a Feynman graph if you take the alpha prime to zero limit. So that loop momentum is the only obstruction to having a factorizing correlator at, say, genus 1 and 2. And let's get rid of this obstruction. Let's outsource this finite dimensional loop integral from that big path integral that defines the correlation functions. So all the integrand results that I will state are tailored to the so-called chiral amplitude, here denoted by this calligraphic F, indexed by leg order n, loop order g. And this is really an open string quantity. It's evaluated at fixed loop momentum, all the simplifications being carried out at fixed loop momentum. And once you have this in an optimized form, then you just square it, loosely speaking. You adjoin a second half of it, and you then perform the loop integral. So this will be the mindset. That's why all the correlators you're about to see are about open string variables, which is tremendously reducing the complexity. So here's a warm-up, approximately 15-year-old result about 2-loop 4-points. The chiral amplitude, so the massless states are represented by gauge boson polarization vectors plus their gaugino partners. And yeah, all the polarization dependence in this 4-point function, it enters in a manifestly gauge invariant way using the linearized field strength. And the contraction is done using the standard T8 tensor as described in the textbook, as you know it already from tree level and one loop in the 4-point function. So what else is around in 2-loop 4-points? Now, these chiral amplitudes are form valued. And since we are at genus 2, there is more than one abelian differential. So we need to take care of these form degrees of freedom for each of the punctures. And it comes out of the calculation in both RNS and pure spinner. that these holomorphic differentials come in anti-symmetrized combinations, these deltas here. That's quite beneficial, both for modular invariance of the closed string, but also for a nice field theory limit excluding triangle diagrams. Okay, so in both RNS and pure spinor, these anti-symmetric combinations were found, decorated by momenta. And this is the hardest part, to find the second line here. But there is an easy part in the first line, which I haven't described yet. This is the so-called chiral Kober-Nielsen factor, simply the contribution from the plane wave, e to the ikx, which are present in each vertex operator. So that's a contribution you can foresee on the spot from bosonic string technology. So since the 70s or 80s, we have been knowing that guy for all loops and legs. So it's essentially some exponential of prime forms together with some decoration by loop momentum. Okay, so I hope that this review is setting the stage for the 5-point result, which is a rather recent thing from last year. So we have found a simplified expression for the 2-loop 5-point chiral amplitude for any 5 massless states. We have them for both gluons and gluinos, since the answer is written in so-called pure spinor superspace. So all the kinematic factors are encoded in certain superfields where a theta variable targets the gluon and gluino components. And if you want to have the specific, say, gluon component, just pick up the right order in theta, which is automatized by now. And apart from kinematic factors, we again have form degrees of freedom. Whoops. So as before, there are these anti-symmetrized combinations, but now in a 5-point function, we are dealing with 5 forms. So yeah, that's why there is one additional omega here. And there's a free index, I, which runs from 1 to 2 over, say, the cohomology. And accordingly, this kinematic stuff has a free index. So this stuff here is what we call the subcorrelator, where all the kinematics can be found. And that free index can, for instance, be placed to a loop momentum. So now the zero mode structure in the pure spinor formalism leaves enough room to pick up a loop momentum. But also you can afford to do an OPE and then catch certain worldsheet functions that are singular as the punctures collide. For sure, we must be careful about the periodicities of a higher genus surface. So what's the periodic way of implementing a simple pole? That's traditionally a logarithmic derivative of the prime form. But since we have already peeled off the form degrees of freedom, you only are interested in the leftover theta functions that go along with the forms here. And so these are the basic ingredients out of which the subcorrelators are made of. I don't expect you to go in detail through the combinatorics. Quite generally, you will see several formula of several similar length. Don't bother to look at them in detail. It's more to give you a flavor of how long these expressions are once we have simplified them far enough. Okay, so the structure is we have a couple of kinematic superfields decorated by certain worldsheet functions with simple poles. And you may ask how to find that. Well, of course, explicit computation is one way. But here in this pure spinor work, we had a kind of bootstrap program to get the exact answer from an ansatz. Namely, by looking into the zero mode structure of the non-minimal pure spinor formalism, we can already anticipate which kind of superfields have the right to participate. So there's a vector building block T and a scalar building block S. Ask me later if you want to see it in full glory. But we can be pretty sure that everything in that chiral amplitude is some permutation of these two guys. And what you can also learn from the zero mode structure in the pure spinor formalism, you can at most have one loop momentum or one OPE. So out of this alphabet of kinematic factors and worldsheet functions, there's not much what you can do, in particular if you impose some consistency conditions like BRST invariance and homology invariance. So let me elaborate on that second point. Ideally, we would love to see a doubly periodic function as the punctures go around the A cycles and B cycles. But since we are in chiral splitting and deal with meromorphic building blocks, we don't get double periodicity. We get certain B cycle monodromies, inevitably, but they are such that they cancel upon loop integration. They can be compensated by a very specific shift of the loop momenta by external momenta. Yeah, so in summary, by combining homology invariants and BRST invariants, we get a unique way of composing the building blocks that were identified by pure spinor calculations, giving a unique result. And that, of course, deserves to be tested. So, for instance, we have checked that you get the correct supergravity amplitude. As a nice bonus, you get the supergravity limit even in a double copy form, where all the kinematic numerators, all the polarization-dependent things, obey the Bern-Carrasco-Johansson duality between color and kinematics. Okay, so supergravity limit is one of the many checks, but needless to say, our chiral amplitude is supposed to get the alpha prime corrections correct. It's supposed to work as far as you have the power to alpha prime expand the integrals. And specifically, we have tested the subleading orders in alpha prime to play out nicely with S-duality of the type 2b superstrings. So we have checked whether the R⁵ interactions that you can read off from the alpha prime expansion, that they do what they are supposed to do by S-duality. And as a particular highlight of the 5-point functions that you don't have at 4 points, you can start violating the U1R symmetry of type 2b supergravity, and say couple 1 dilaton phi to 4 gravitons. And this is an extremely interesting corner of type 2b amplitudes violating R symmetry, which are purely stringy effects, and which in the full duality invariant picture are associated with modular forms of the axiodilaton. And I think we have seen something about that in Concal Ben's talk yesterday. So these are some checks of the 5-point function, which also constitute the motivation that there are a lot of interesting new aspects at 5 points, which you don't have a fair chance of spotting at 4 points. So this is a major motivation why it's important to have control in the multi-leg regime. Yeah, so this was about pure spinor-induced result for 2-loop 5 points. There is an ongoing RNS calculation. Okay, let's say we already have a result, namely that a first principal calculation in RNS for the external bosons is giving the same result as doing pure spinors and then extracting the external bosons from the theta integral. So this is to say we have another high loop, high leg case of where RNS and pure spinor work out together and give the same amplitudes. Now, giving you more details of the calculation, maybe we leave this mostly for the private discussion. We have been using the same kind of formalism that Eric and Fong used 2005 to compute the 4-point function. And of course, it's a bit more work to do. That's at 5 points, more sums over the spin structures, and more work to be manifestly independent on the gauge slice, namely the locations of some supercurrent insertions. Okay, and one multi-loop highlight, which is a very, very recent paper. This concerns 3-loop 4 points. There is an impressive proposal by Yvonne Geyer and Ricardo Montero and Ricardo Muchao-Stark. Just came to the archive 3 or 4 weeks ago. So these guys have started from ambitwister arguments and have found a beautiful construction to come up with a proposal to the full-fledged chiral amplitude for superstrings, which you can use to alpha prime expand as high as you have control on the genus 3 integrals here. So some of the things may remind you of the 2-loop results. So here is a delta similar to the anti-symmetrized differentials at 2 loops. Now it's a 3x3 determinant. And maybe the most subtle corner of the proposal is here, where you have a bunch of Sager kernels. So these are the fermionic 2-point functions in the RNS. And of course, we ultimately want to sum them over the even spin structures of the worldsheet fermions. And yeah, the spin sums have not yet been evaluated for us, but the authors have precision control on the degeneration limits of that contribution here. So they have given good evidence why this is a good choice. And yeah, the chiral measure made of chi8 and psi9, sorry, not for defining it here. So these ingredients have already shown up in earlier literature, not only here, but also similar expressions have been seen in work of Eric and Fong from 2004. Yeah, so this is the recent proposal for the full chiral amplitude. And of course, we already have an impressive 3-loop result from 8 years ago, done by Carlos Mafra and Humberto Gomez, who computed the low energy limit of 3-loop 4 points and showed that the d to the 6 r to the 4th contribution ties in with S duality. So Carlos and Humberto had a substantial part of the chiral amplitude on the previous slide. Namely, they had the contribution which does contribute to d to the 6 r to the 4th. But that stuff below here, this only kicks in at higher order, namely d to the 8 r to the 4th. That's why it wasn't needed in earlier work. But instead, this contribution down here is crucially contributing to the super Yang-Mills and supergravity limit. It has crucial contributions to the Feynman diagram numerators, say for a tennis court graph depicted here. And this was actually the driving force how Ricardo Square and Yvonne got their proposal. They insisted that these Bernd Carrasco-Johansson dual numerators should pop out in the degeneration limit. And this is what they managed to use constructively to build up the correlator. And part of the deal was to have a good nose for the modular forms that you need to decorate it with. I mean, it's in the heart of the ambi-twister method at work that in the first place, the field theory numerators give you a certain degeneration limit. But the proposal is for generic values of the omega AAs. So it's the nose for the right kind of modular form that allowed Yvonne and Ricardo Square to really go to a generic point in moduli space. Yeah, so this is a really cool example of how ambi-twister methods succeeded in giving a highly useful input for conventional strings at finite alpha prime. So this brings me to the end of the integrand part of this talk. So now for the rest, I will consider the chiral amplitude to be there and tell you a bit about the leftover job to perform integrals, and specifically order by order in alpha prime. So let's switch gears to the integral side. And this is a good moment to get rid of the loop momenta. So we have the loop momenta in the form of Gaussian by virtue of the chiral Kober-Nielsen factor. So we can, without much trouble, perform a Gaussian integral over loop momenta. And this is the moment where modularity can occur or can be manifested. So if you arrange the result of the loop integral and the Kober-Nielsen factor in a good way, you get a modular invariant Green's function, the so-called Arakelov-Green's function, if you make use of momentum conservation. So this is, if you wish, a higher loop version of the logarithm that you know as the Green's function at genus 0. And say at genus 1, that Arakelov-Green's function is a certain completion of log theta 1. And it's engineered to be, among other things, modular invariant. And it's engineered to integrate to 0 with respect to a suitably chosen volume form. So the alpha prime expansions that I will describe in the subsequent slides, it concerns the result of expanding that exponential and integrating polynomials in Green's functions. This is admittedly a very rough approximation. There are in truth some poles and logarithms in the Mandelstam invariants that are there by unitarity, but I will mostly ignore them for now, and we can discuss in private how you can reinstate that. Good, so let's see what you get by alpha prime expanding here and integrating over the punctures of the Arakelov-Green's functions. So on this overview slide, I want to do some name dropping for the function spaces in which you will find yourself as you integrate out the punctures. So I will keep the surface fixed. So I will keep the moduli or period matrix entries as unintegrated for the moment and tell you which kind of modular objects you will get. But let's also look at the open string side where you you restrict the Arakelov-Green's function to the boundary of the open string worldsheet. So there, for open strings at tree level, integrating the punctures gives you multiple zeta values. I guess you all know the Riemann zeta value with a single subscript. And here is a multi-argument generalization thereof, which is really a prominent object in number theory. So the multi-zetas, you really need multi-arguments from the 5-point function onwards. And for closed strings, it's no surprise that for closed string tree level, you again have multi-zetas, say by looking from the distance at KLT. But now there is a cute selection rule, which you don't see on the spot from KLT. There are many dropouts. The closed string tree level amplitudes, they only have the so-called single valued multi-zetas, where to zeroth approximation, you drop the even ones and you preserve the odd ones. And you do more funny things at higher depth. And this may look a little bit like black magic, and I would in fact need a motivic setup to make this even well-defined. But let's gain some physics intuition about what this single valued map is for multi-zetas. Let's recall the prehistory that the multi-zetas come from logarithms or polylogarithms evaluated at unit argument. Imagine you integrate out the punctures one by one, and you go on strike before you integrate out the last puncture Z0. So in this almost last step, you will have polylogarithms, say in open string tree level. And polylogarithms are notoriously multi-valued and have nasty monodromies as you go around the origin or Z=1. And on the closed string side, these polylogs want to conspire to single-valued objects where you need support from the complex conjugates. And this is a way to define what a single-valued multi-zeta is. It's what you can get by evaluating single-valued polylogarithms at unit argument. So there's a single-valued map which commutes with evaluation, so to say, and which gives you a fully explicit construction. You start with open string data, you hit the multi-zetas with a single-valued map, and you get the closed string results for free, for the moment at tree level. And for sure, it's an appealing scenario to get closed string results for free also at higher genus. So that's why we find it essential to think about a higher genus uplift of a tentative single-valued map. To also do this, say, with functions of the modular parameters that you get when you start integrating open string punctures over a cylinder world sheet, as it occurs at genus 1. So as you go to one loop, the function space of configuration space periods is getting way more interesting, involving, say, elliptic multiple zeta values, elliptic analogs of polylogarithms. And then on the closed string side, there is a beautiful system of non-holomorphic modular forms. So my apologies that the box is getting too small to spell out the names Doker, Green, Gürdogan, von Hoof, and also Doker, Green. And by comparing what you get from the open string case and the modular graph forms on the closed string side, there is a proposal on the horizon to do a single valued map really for the functions of tau that you get after integrating out the open and closed string punctures. So we are also at one loop on our way to get the closed string results for free by throwing suitable operations on the open string side. And yeah, also the closed string modular graph forms have an origin from functions of more variables. So here, these are certain generalizations of single-valued elliptic polylogarithms, investigated by Doker, Green, Piolin, and investigated by Doker, Kleinschmidt, Schlotterer. Okay, there's an obvious question in the air, how this graph goes on for higher genus. For the moment, I can only report on what has happened on the closed string side when all the punctures are integrated out. As far as time permits, I will tell you about higher genus versions of modular graph forms. So these are modular invariants or modular forms, certain modular tensors of non-holomorphic type, yeah, which I believe will have a lot of fun questions and answers that are of equal interest to string theorists and mathematicians. Yeah, so this is a zoo of interesting configuration space periods that you encounter naturally as you perform alpha prime expansions of string amplitudes. And the mastery of these function spaces is essential to get access to low energy effective actions, to do precision tests of, say, S-duality of type 2B.
Ali, you have about 10 minutes left.
Thank you, Eric. Good. So I have a couple of details ready on, say, the one loop specific cells of the overview figure. In view of time, I will be rather brief. So what should I tell you about elliptic polylogarithms that arise on the open string side? So this is a natural generalization of the polylogs at genus 0 that Anastasia described for you yesterday. You saw in Anastasia's talk that polylogs at genus 0 are iterated integrals over D-log forms. So the D-log forms being tailored to the sphere. Now at genus 1, you need to find an analog of D-log, which is tailored to the torus instead. And the genus 1 version of D-log, it's in fact an infinite number of integration kernels Fk that can be nicely generated from this Kronecker-Eisenstein series up here. So the elliptic polylogs built from that have been studied in mathematics, and it was a wonderful fit because on the string theory side, these Fks turned out to be the universal currency for correlators in genus 1 cases where you have vertex operators on the torus. So here the Fks were, say, the common fun gadget to both mathematicians and string theorists. And also to particle physicists, this system of elliptic polylogarithms was really valuable to significantly push the research frontier of which Feynman integrals can be evaluated. Of course, there are many Feynman integrals that go far beyond the elliptic reach, but it's definitely a lot of progress to have the elliptic polylogs for, say, sunrise diagrams and alike on the Feynman diagram side. Now, a few more words about the modular graph forms. So for the closed string, you have the job to integrate Arakelov-Green's functions over the torus and also these integration kernels Fk. And both of them are doubly periodic functions tailored to the A cycle and B cycle of the torus. So needless to say, you can Fourier expand in the two real coordinates u and v on the torus. And in this double Fourier expansion, you get lattice sums of the form written down here. And you can interpret this as doing Feynman graphs on the torus. You can interpret these denominators, m tau plus n, as two-dimensional discretized momenta. So these modular graph forms, yeah, they arise from scalar field theory on the torus. And it's an intriguing system of non-holomorphic modular forms. So you have these absolute value squares here for the Green's function. And as you integrate more and more of the Green's functions, you get more and more of these lattice sums. So it's a bit like doing a multi-loop Feynman graph on the torus. Though in string perturbation theory, this is still genus 1. Okay, so this is to give just one sample of how such modular graph functions look like. And there are a lot of surprises, such as how many summation variables do you really need? There are many situations where you can simplify and say, remove some of the summation variables in favor of a simpler sum in the second line. So there are many relations among these modular graph forms that are far from obvious to the lattice sum representation. This is one of the many reasons that this is an exciting subject to, say, classify the independent modular graph forms. And yeah, further crucial properties are that their Fourier expansion involves multiple zeta values. To the best of what we know, it's just the single valued ones. And since we are dealing with non-holomorphic modular forms, you can expect a really vast space of them, because it's only in the holomorphic world that the modular forms are easy to count. Okay, so there are these modular graph forms on the closed string side and elliptic multiple zeta values on the open string side. And I talked about this idea of a single valued map, which takes you from open to closed strings, which takes you from elliptic multiple zeta values to modular graph forms. So in order to have a chance to do that, you need to have a language that applies a little bit to both of them. And the language that does this job, it concerns primitives of holomorphic Eisenstein series. So both sides are iterated integrals over holomorphic Eisenstein series. I should be really schematic here, but the upshot on that slide is you are well advised to use this language of iterated Eisenstein integrals. This, first of all, exposes all the algebraic and differential relations that the modular graph forms may have. And it secondly builds the bridge between open and closed strings. And it furthermore builds the bridge to mathematics. The master of iterated Eisenstein integrals, at least from our string theory perspective, is Francis Brown, who had a series of beautiful papers on iterated Eisenstein integrals and their single-valued versions. And it's an ongoing process to get the best out of Francis' work.
Yeah, you have about 5 minutes, Alex.
These iterated integrals are what helps you to go from open to closed strings at genus 1. And we want to do similar things at higher genus. So let me give you a schematic impression of what modular graph forms at higher genus are, approximately. So you can, again, integrate polynomials in hierarchical of Green's functions. But now you have a lot more integration measures for choice. So now you have a G vector of abelian differentials on a genus G surface. So there is now a combinatorial layer, which kind of measure you want to use, in which way you contract the indices I and J that you don't see at genus 1. So the groundbreaking papers on modular graph forms are essentially those up here, where the simplest example has already been studied for a while and used to do impressive explicit checks of S-duality. You can go even wilder and generalize the modular graph forms to tensors, but maybe I shouldn't go into much detail in view of time. But the cool thing to say about modular graph tensors is that you take the most general integration measure that you may reconcile with modularity. And these are auxiliary objects that are super valuable to study the relations between the scalar modular graph forms. So even if you didn't have the intention in the first place to study tensors, it is rewarding to do so nevertheless. So here is one relation to show off among the scalar modular graph forms. And in order to prove it, the only method we know up to date is to use the tensors as an auxiliary object to carry out a brief proof. But who knows what further methods will hit the market as the months and years go by. All right, I have been shamefully neglecting the gravity sector of type 1 superstrings. There are, of course, disk diagrams and cylinder diagrams with closed string insertions, as you study the, say, Einstein-Young-Mills sector in type 1 and all the alpha prime corrections to that. So these are further classes of configuration and moduli space integrals where exciting progress has been attained. So let me go through the tree-level version where Stefan Stieberger and Tom Taylor had important papers. So there, the gist is that a closed string insertion in the bulk of the disk can be traded for 2 open string insertions on the disk boundary. More details you find in the reference. And the same kind of integrals over the upper half plane, which is a nice parameterization of the interior of the disk, the same kind of math technology appears in deformation quantization, where there was a really beautiful paper by Banks, Panzer, and Pym, where they applied a variant of single-valued integration, and where you can see that it's similar math in perturbative string calculations and corrections to Kontsevich star products. And yeah, the reason why this is timely is that Stefan Stieberger had a recent paper of doing these mappings at genus 1 to map a closed string insertion on the cylinder boundary to a doublet of open string insertions on the boundary. I'm sorry, I should have said in the bulk of the cylinder for the closed string. Okay, so there's really a lot to do also in the gravity sector of type 1, and exciting progress just happened recently. Good, I'm supposed to wrap up soon. There are so many topics where I feel really bad that I haven't touched upon them. Maybe the most pressing one in view of all the configuration space integrals. I haven't finished the job and I haven't integrated over tau or say the complex structure moduli at higher genus. But you get very close to doing that last integral if you know about Laplace equations and Poincaré series of modular graph forms. And I realized that it's hopeless to go through all these bullet points. My apologies for directly hopping to the last slide. So these are the key messages I would really love to drive home. So you saw in this talk some examples of recent progress on string perturbation theory, focusing on explicit evaluations of massless string amplitudes, ranging from genus 0 to genus 3, 4 points and 5 points. And so much of that recent progress was owed to mixing sources of inspiration on the RNS front, on the pure spinner front, and also getting input from our ambi-twister friends. And you also heard new results on the mathematical aspects of doing the integrals over punctures, where crucial inflow from mathematical ideas has helped a lot. And you may complain that most of this has been at finite order in perturbation theory, at low order in alpha prime. Maybe some of you have missed the impact on non-perturbative physics. And let me mention one aspect about this, which is tied to the non-holomorphic Eisenstein series that you saw in Konkao Wen's talk. The non-holomorphic Eisenstein series at arguments 3/2 and 5/2 is describing the exact type 2b couplings of R to the 4th and D to the 4th R to the 4th. And there are pressing questions of what comes beyond E3/2 and E5/2. And we know one more layer from D to the 6th R to the 4th. And I believe that a good toy model for this function space of the non-perturbative completions in type 2b, I believe a good toy model are the modular graph forms, which are, if you wish, the non-holomorphic Eisenstein series at the integer arguments. So what we have to learn is how to take the most general modular graph form and go into the half-odd integer world. And this will give a candidate function space for the non-perturbative story in type 2b. So that is why I expect a vast impact of this over the next years. But for this, there's definitely a lot of help needed. So I hope that this talk could motivate some of you to join us in all these adventures for the future. I should really stop. Thank you for your patience. That's it.
Let's thank Ali for a beautiful talk. And maybe unmute. So now the floor is open for questions. So Nathan.
I would like some more details about this ambi-twister proposal. Can you say a little bit more about what has been checked and what are the ingredients used for constructing the expression?
Okay, let me try starting from here. Okay. Yeah, so the ambi-twister approach at loop level, it has certain scattering equations for the complex structure moduli that localize you on this degeneration limit, where the diagonals go to I infinity and where the A cycles pinch. And then your genus 3 surface is mapped to a multinodal sphere. So here for 3 loop 4 points, this is a 10-point sphere diagram. And there is a standardized prescription to convert these Bernd-Carrasco-Johansson numerators into a correlation function on the sphere. So we know exactly which 10-point correlator on the sphere we want based on the BCJ numerators. And now the next step is the big adventure, how to reverse engineer which function in generic points of moduli space has the right limiting behavior. What is the original expression that gives the 10-point correlator on the sphere in its degeneration limit? And then I guess that Ricardo, Square, and Yvonne were playing a bit of trial and error games, writing down various modular forms where they know their degeneration limits, and they adjusted the relative coefficient until it really reproduced the BCJ numerators.
But does that claim to uniquely define this? I mean, so it agrees in some limit, but is that enough to uniquely define the 4-point amplitude?
It's unique to the extent that the space of modular forms is unique. I don't know whether this is true or not. Okay. And in particular, if you find cusp forms that can contribute here, then these cusp forms cannot be determined from the nodal sphere limit. So okay. To the best of my knowledge, it's not unique, but I hope that one of the authors is in the audience to contradict if necessary.
Thank you.
Hiroshi?
Yeah, thank you. So very nice talk. So, so I have a question about the comparison with the S-duality predictions that you mentioned. I guess you are referring to a coefficient of higher derivative terms such as product or curvatures. And I guess you are yet to do the integral over base Riemann surface moduli such as tau. So before you do that, how would you make such comparison?
So if you allow me, I will try to answer your question at the level of a two-loop 4-point example. So this is the chiral amplitude for the open string half. Then you square it to get to the closed string. And by just looking at the polarizations and the momenta, the low energy limit for the closed string is already d to the fourth, r to the fourth. So if you now set the momenta and the Koba-Nielsen factor to 0, then all you have to do is integrate these deltas over the moduli space, meaning you integrate over the punctures that give certain imaginary parts of period matrices, and then you catch the volume of moduli space. So in the low energy limit, it's, if you wish, just the volume of the genus 2 moduli space of period matrices. But the difficulty level goes up as you take the external momenta from the Koba-Nielsen factor, as you pull down these Arakelov-Green's functions. Then it's getting substantially harder to do the Z integral in presence of the Green's function. So at the subleading low energy order, this is d to the 6 r to the 4th, your task is to integrate this Chang-Kawazumi invariant written down here. So one Green's function, as I promised, taken from the Koba-Nielsen factor. This is the unique measure that is non-vanishing along with the Arakelov-Green's function. And after you have integrated the punctures Z and W, you're supposed to integrate this over the moduli space of 2x2 period matrices. And for this, there's a beautiful work by Eric, Michael, Boris, Rodolfo, where they did it using a Laplace equation with respect to the moduli. You can trade this Chang-Kawazumi invariant for a Laplacian plus a contribution that localizes on the separating divisor. So this is a case where the full integral has been done, where the coefficient has been worked out and matched exactly with the predictions from S-duality. So on the S-duality side, this is a function of the axiodilaton along with d to the 6 r to the 4th that obeys an inhomogeneous Laplace equation. Laplace minus eigenvalue of the thing we want equals the square of E3 half. And there is, I think, some work by Green van Hoof where they worked out all the perturbative terms of this S-duality invariant.
Okay, I didn't realize that in these cases you can't actually carry out this integral. And so do you get the coefficient right on the nose?
You get it right, yes. By this paper here, you get it right.
Thank you.
Okay, are there other questions or comments for Ali? Edward?
I have a small comment just about the genus 3 proposal. I think that the question of whether the holomorphic formula is unique is slightly premature. There's a very fundamental question of whether such a holomorphic formula should exist. That's extremely unclear, at least from the RNS formula. Because, for example, if you integrate over odd moduli, keeping fixed the superperiod matrix, you don't get something holomorphic. There might be some framework that gives a holomorphic formula, but explaining why that is true would be fundamental.
Okay.
Thank you for your comment. Ali, do you have a...
Nothing to add to this. Thank you, Edward.
Okay. Any other questions or comments?
Maybe I can just say from the pure spinor framework, it's also, if you go above the low energy, it's also tricky because then you can start getting the subtleties from the lambda bar poles. So.
Right. So this low energy analysis, it had terms of the B ghosts, which were not too divergent in lambda lambda bars, where say milder regulators were enough to do the job.
Piotr?
Yeah, since you're on this slide, or the one before maybe, with the 3-loop graph amplitude. So didn't Carlos also had a non-zero mode term in his amplitude, like the yi mu that you write? I thought he had a derivative of the propagator in there as well, while in their proposal it appears only in the blue term.
Okay.
So I'm wondering if Carlos' term mixes both the red and the blue, or if everybody thinks it's really just the red term. But it would be better to ask this question to the authors directly, I guess.
Mm-hmm.
Yes, maybe. I think in view of time, we may have to move on, and perhaps this question can be relegated to the Slack channel discussion. So let's thank Oliver again. And we will now move on to the last talk of the day by Lorenz Eberhard. Lorenz, can you?
Yes. Can I just
share?
override you, Oliver, or how does it work?